computer. Hello, good evening. It's May 5th, 2020. It's our series of lectures on modeling and simulating earthquakes, soil structures, and their interaction. Today we're going to talk about energy dissipation. Together with me are Dr. Han Yang, who's going to talk about energy dissipation. That's work he's been doing over the last few years. And Mr. Heshen Wang, who is going to contribute this time with some questions and comments. And actually next time he's going to talk a little bit more about some probabilistic modeling that he's actually playing with. My name is Boris Jeremic, and we'll start with Han. So Han, please take it over.
Yeah, thank you. Okay, so first let me share my screen. There we go.
Good.
And full screen. All right, can you see this?
Yes, great.
Yeah.
Okay, all right, so thank you, Professor Boris. So today we're gonna continue our lecture. So today I'm gonna talk about the modeling of energy dissipation in earthquake soil structure interaction systems. So this is the part one of a series of lectures on this topic. So this part one is the introduction part. So here is an of the entire lecture series on this topic. So first we're gonna go through the introduction part. I will talk about the motivation, some of the issues in the current practice and the objectives of this study. And then I will go into details to talk about the theory and formulation of how to calculate each energy terms, including the input, the dissipation in different kind of elements and materials, and then different mechanisms of energy dissipation. Then in the last lecture, we will talk about some application examples. So here, in the first part, we're going to go through the introduction. So this is today's topic. So first, let's start with the motivation. So the main motivation behind this work, like why do we even care about energy dissipation? The fundamental answer to that is that the energy dissipation is directly related to material damage. So for example, in this simple example I'm showing right here, we have a frame structure that is loaded with some seismic shaking. So as you can see, the color red represents the amount of energy dissipation, which is also representing the material damage happening in this case. So for a beam that is loaded like this, usually so-called plastic hinges will develop, and within those plastic hinges there will be material damage, permanent deformation, and also energy dissipation in the form of heat. So the point here is that if we can properly dissipation in like structures and soils, we can actually track the material damage, and that is a very important information in engineering designs.
Can you go back? I'm sorry. Can I just so essentially the idea is to change the design so that you can direct for given earthquake, and then you can try different combinations of earthquakes, different motions for a given set of motions, to change the design in such a way to dissipate energy, to damage the material, damage the structure and the foundation and soil if you care about that, in a way that you as a design engineer want to damage it, as opposed to the way you design it and you hope for the best. We actually want to be able to model this, and in this particular case you see that a lot of dark red is down in the foundation, so that soil gets damaged, so to speak. Damage in soil really means that it's just plastifying a lot. And we don't really, I mean, this is okay as long as we know that it's going to maybe move more, there will be more displacement. So as long as we can design our system to accommodate more displacements, then we're okay. And you'll see toward the end, and the same example with different type of foundation, that it actually reduces a lot the amount of damage, the amount of dissipation that happens in those beams. And that's, in this case, what we care about. We want to limit the damage in the structure and maybe put the damage down or put dissipation down into the soil. Anyway, so I'm sorry, go ahead.
Yes, that is absolutely correct. So later we will actually revisit this example and to directly show you how changing design can result in the change in energy dissipation. So So here are some of the advantages of energy-based design. So on one hand, we have the traditional force-based and displacement-based design concept that are mainly focused on a peak response, not a loading history. And also, it's often oversimplified some nonlinearity and inelasticity. But on the other hand, we have the energy-based design concept that are focused on accumulative damage during the entire seismic event. It is time history dependent. It is intrinsically modeling the nonlinear and inelastic behavior of the materials. And it is very important for ductile failure because it tracks the accumulated energy dissipation and damage. So next, we move on to some of the issues in the current practice. So here, what I'm showing you is one of the most commonly seen oversimplification in this field of study. So here we have a complex and tall and big building, but in many studies, it's modeled as a simple multiple degree of freedom system. So basically we simplify this complex system into just a mass and stiffness and some kind of dampers at the bottom. So with the development of modeling and simulation tools, we can actually do a much better job than that. However, in the energy-based design field, this oversimplified modeling is still a predominant problem. So we can definitely improve on that.
And just to interject here, so
yes,
these simplified models might be okay, but one has to be able to show with a more sophisticated model that these simplified models, which can run very fast, are able to model all the details of what is of interest to engineer. If they cannot model that, for example, if it's a single degree of freedom system, you cannot model second mode. Maybe second mode is important. Things like that. And of course, these sets of dampers and springs at the bottom, I'm not sure that they actually represent properly the behavior of soil and radiation damping and viscosity of the system and so on. So they might be okay for some analysis, but you have to be able to demonstrate that they're okay. And to demonstrate, you have to be able to go to 1 or 2 levels of sophistication higher and show that those simplifications are not destroying your results. Go ahead, I'm sorry.
Right, yeah, no problem. So yes, so that is one big problem, the oversimplification. So next we move on to a more technical issue here. So this is what we have been taught in like for a really long time. So for example, if we have a stress strain loop that looks like this, and then we have been taught that the energy dissipation per each loading cycle equals to the area enclosed by the hysteresis loop. So basically, if you have a loading that goes one cycle, and then you say that, okay, this area, this red area here is the amount of energy dissipation per that loading cycle. But however, that is not correct. And later we will demonstrate why this is not correct. And then just to go one step further, because you don't always have a perfect hysteresis loop. So then in the case of an evolving hysteresis loop, and even more extreme when you have monotonic loading, like in this kind of case, what do you do? So to extend that definition of the area, so we use the incremental equation that says the incremental energy dissipation at a specific loading step equals to the stress tensor multiplied with the incremental plastic strain tensor. So note that this equation is in fact consistent with the hysteresis loop definition. So which means that if this equation to calculate a perfect loop, then you will get the area. However, the same as before, this is still not correct. And again, we will talk about that.
Yes, so this equation is what I remember from school. Essentially, everybody thinks that this is plastic dissipation. It is not. It's a plastic work. Yeah, I'm sorry. Go ahead. Yeah.
Yep. So let's first look at what would happen if you actually use that equation, and that happens a lot in literature. So this is an example we obtained from one of the many famous papers. So here what we have is a simple frame structure on top of some base, and then we apply some shaking at the bottom. So basically the researcher was tracking the force displacement response and the energy response of the system. So here, let's focus on this thick black line right here. So the researcher claimed that this is the accumulated energy dissipation throughout the entire event. And we can see here it's increasing with some fluctuations, but the fluctuations actually is a big problem, because if you think about it, when you decrease, you actually have a negative incremental energy dissipation at those certain time steps. And that is a big problem.
Yeah, which is impossible.
Yep. So a negative incremental energy dissipation means that at those time steps, you actually have energy production. And that is a direct violation of the second law of thermodynamics. That is impossible. So something was wrong there. So the source of that problem is actually the misconception between plastic work and plastic energy dissipation. As Professor Boris mentioned before, those two are not the same. And the difference between them is a very important energy form called the plastic-free energy. Yes. And of course, we will talk about the plastic-free energy, the source, and how we calculate that. Okay, so here, let me just move on to kind of a bigger picture. So the entire process of the propagation of seismic energy from the source to our local site. So we know that at the rupture of earthquake, there is a huge amount of potential energy released at the earthquake source. Now, and then this amount of potential energy will propagate in the earth with the seismic waves. So we know that during that process, there's a huge amount of energy already dissipated with the scattering of the waves and the elasticity of the rock and soil. So there will be a certain amount of mechanical energy that reaches to your local site, and this is where our interest starts. So this is the scope of our work here. So when this mechanical energy reaches to your local site, it will be transformed and dissipated into various forms. So first, we have a small amount of the energy that is still in the form of mechanical energy that is stored in the system. This is the part of the kinetic energy related to the shaking. This is the strain energy, elastic strain energy. And then we also have a certain amount of the mechanical energy radiated out of the local system together with the outgoing seismic waves. And then on the other hand, we have various mechanisms for energy dissipation. We can have the inelasticity in the structure that contributes to structural damage. That's something we care about, care about very much. Then we have the inelasticity in the soil. We also have the friction slipping in the contact interface region between the structure and the soil. And also we can have viscous coupling in the soil if the soil is saturated or partially saturated. And we can also have artificial energy dissipators in the structure to help the structure to resist seismic events. Then of course we have the tricky component, which is the plastic-free energy. So this is the scope of this work. We're trying to basically model and calculate the energy transformation within this process.
To be able to account for all these components of energy. That's the point. Yes, go ahead.
Yes. Okay. So here, just to, as part of the introduction, just to give you some of the explanation history of the plastic-free energy term. So this term of plastic-free energy was first discovered actually in metals in a study by, actually in a series of studies by Professor G.I. Taylor and his colleagues going way before, as far as 1925. So in his experiments, he applied some loading and then generated some plastic deformation on the metals. So in this figure here, it's actually showing two things. So this axis on the left side, showing the percentage of plastic-free energy out of the total input work. And on the other side of the axis, we're showing the stress. So from the stress curves, we can see that there's definitely some plastic deformation. So that means there will be plastic work and plastic energy dissipation in this study. So here, those dots demonstrate the percentage of plastic free energy out of the total input work, we see that in this specific case, there's about 10% of the total input work that is transformed into plastic-free energy. Now, it is important to realize that this number, 10%, is just for the specific case. For some other materials and some other loading cases, the plastic-free energy can actually be much more predominant. We have observed this number go up to like 30, 40, or even half of the total amount of input work. So the point is that we should always account for it. We shouldn't just simply neglect that. So it's a very important form of energy in this case. Okay, so after the discovery of plastic free energy in metals, so now in our field, we also care about granular materials like soils, sand, and other geotechnical materials. So in those kind of materials, the plastic free energy is actually even more important because it can be attributed to the multi-scale effect of particle interlocking and rearrangement. So basically, the physical nature of plastic free energy is the strain energy on a particle level. So this is a simple illustrative example to showing you the idea of that. So here what we are seeing is that basically an assembly of particles, and at the beginning, so let's focus on this particle A right there. So let's imagine this particle A here is only in contact with two other particles. Particle A is only weight. And now, at this point, is only bearing its own self-weight. So that means that the strain energy on the specific particle is actually very small. But then let's imagine some loading is applied to this material. And then this particle B here is being pushed into particle A, and then even further, this particle A is now stuck inside this void that is formed by these other particles surrounds it. So at this point, this particle A not only bears its self-weight, but also the external load, which means that the strain energy stored in this particle is much higher. So compared to the original state. And later, even if we unload this material, because of this particle now being stuck inside this void, the strain energy that was increased in this particle will not be totally released. So compare this end state with the initial state. Even if the stress and strain on the macroscopy level might be the same, but on the particle level, the strain energy actually changes, and it can change a lot. So this part of the strain energy on the particle level is the physical nature of the plastic free energy in elastic plastic materials.
Yes.
Okay, so now we have identified the plastic free energy and the importance of it. So we can say, okay, that the original definition of this incremental equation as the stress tensor multiplied with the incremental plastic strain tensor actually describes the plastic work. So the actual plastic energy dissipation, the calculation of that comes from the by subtracting the plastic free energy from the plastic work. And later in the next lectures, we'll talk about exactly how you calculate each of those terms for different kind of material models. So the overall objectives of this work, of this energy-based design is here. So whatever we are trying to build is a system for computation and visualization of energy-based design. So our main tool here is the Real Easy Simulator. You have seen the explanations of that in our previous lectures. So by using Real Easy Simulator, we can compute and visualize the energy dissipation happening inside your system, and then use that information. We can identify material damage by looking at the energy dissipation, and then one step further, we can improve the safety and economy of engineering designs. So here is the same example. Excuse me. So here is the same example we presented at the very beginning, just to show you how this information can be used in engineering designs. So we have this 2D frame soil structure interaction system. We have the frame structure on top. We have the soil underneath, and then we also have the contact interface element between the foundation and the soil. So a very important part here is that even though this is a simplified 2D model, but it is a code-conforming design, all the material parameters are carefully calibrated, so the information we obtain from this example is actually very informative. So here we are directly comparing two different designs of the foundation. On the left-hand side, we separated foundation design. So basically, underneath each column, we have a smaller foundation. On the right-hand side, we have a larger continuous foundation beneath the whole structure.
So a classical difference between the spread foundation on the left side and the slab foundation on the right side. And you know, some designers prefer one over the other one. But if they had a tool like this, they could maybe make a decision based on the damage. So yes, go ahead.
Yes. So now, if we apply some seismic loading, some shaking into those two models, and then we calculate the accumulated energy dissipation. Remember, we mentioned that that is also damage. So we can actually see the difference that's happening in those two different designs. So in this separated foundation design, we see that in the soil right here, this yellow circle, we see that comparing this case with that case, we see that the energy dissipation in the soil is much less than in this case. The same thing happens for the contact interface. So much more, but then on the other hand, much more energy is dissipated in the structure itself. So if we look at this green circle, we see here much more damage and energy dissipation is observed in those beams and columns. So in this specific case, we can see that by changing the design of the foundation, we can actually direct the location of energy dissipation. So in this case, we have much more energy dissipated in the soil and in the interface. So that means less damage in the structure, and that makes your design safer from the sense of energy dissipation.
Yes, and in this case, of course, there's also a difference in stiffness of the left spread foundation is less stiff than the right side. But in this case, I think that stiffness also contributes, but mostly it's the dissipation of energy in the foundation part on the right side that contributes to far less damage in that type of structure. Yes, go ahead.
Yes, so basically this example just to illustrate what kind of result and what kind of information we can obtain from the energy dissipation analysis. So this kind of things we can do for all kind of structures and complicated systems. So this would be the objective and the kind of expected result we can get from this kind of analysis.
Thank you very much. So we'll stop here and then we'll continue. Yes, I'm sorry, go ahead.
Yeah, yeah, so that was the first part of the, just briefly, so acknowledge my collaborators and funding resource. And for more information, please go to the website of the Real Easy Simulator.
Thank you. So we'll stop here and we'll be back with the next lecture that actually talks about calculation of how is this done for solids. Okay, I'll stop recording right now. Goodbye, everybody.